All right, I'm gonna try this again here. Thank you for tuning in. Yeah, just I can't really, wrap my head around the Penrose, uh, like if it whether it's like a light bulb and the inversion of the light bulb is sort of your equation for anti-gravity. Um, and then these like meson particle splitters, meson anti particles, and so I mean, there's nothing really that I can derive that is, for me, it's just one or the other. It's just a flat plane, or it's the 3D plane. It's just the flat plane or the 3D plane, and I can't really. I mean, this is my point. Like, I'm just trying to progress into just a nuclear physical idea of uh, small universe, Earth, and how essentially gravity can work in that sense. So to me, that is just where you have uh, quantum gravity and just this idea that there is a higher amount of bits in the closed gravitational space, and then the further you move outside of essentially that orbit of magnetism, then that's when the bits start decreasing, but the energy in between the bits, or sorry, the distance between the bits increases. So the magnetism essentially has to uh, fuse. And so there's going to be a higher degree of fusion. So essentially, it's the potential energy thing again, but that's how the low volume of what entropy was at the static state Big Bang. Uh, there is low volume at that essentially because for that reason, since it is a paradox. And I wouldn't say that that's my opinion. That's science's opinion. That's physics opinion. And yeah, like, so you're just talking about, like, I mean, whether it's the Earth's gravity or you're trying to do like an antenna, uh, sending out like a radio wave, essentially. Uh, it makes sense that those radio waves, if they are um, disturbed, then, well, they're going to be disturbed by larger quanta of bits, and therefore the signal, like the antenna and the connection, or not the connection, but rather just all these, they're just uh, anthodes and cathodes, and the anthodes and cathodes. um, sorry, this magnetic effect or the electromagnetism that can somehow be able to propel like a signal, like through alternating current. Like, you'll have one stop at the bottom of the antenna and another stop at the top of the antenna, and then at the top of the antenna, that's where the signal is let off, gravitational waves, and it can only be disturbed either through decay or through essentially bigger quanta of matter. And then you also have I'm just checking if I can. I'm just checking if I can hear myself. Okay. So then you have this like dielectric effect where the so there's one monopole that's sending off magnetism, and then there's this nuclear uh, fission is going to be a while. It's going to take me a while to actually be able to say that correctly. But yeah, nuclear fission is happening, and then there's actual nuclear fusion. I mean, you could say that's what's sort of paradoxical about this uh, low volume Big Bang static state theory, because it doesn't have to have, like you're not really predicting. Well, if you're predicting if it's going to get picked up by another uh, antenna, like a car antenna is going to pick up the radio signal, and the radio waves get there uh, easy enough, then I mean, you could somewhat call that like this Faraday paradox or magneto-dielectric effect, and that's just observable because then your fuse is already your fuse has already been enchanted. I mean, you can't really say that's not accurate. Like that's not a essentially a fifth dimension, because if you count the three dimensions that you see, the dimension of time and then another dimension of essentially force, you're saying, well, that's a dielectric effect, so that would be a fifth dimensional theory. Like if you had two of these antennas, you're saying that's a nuclear fusion, or like a the magnetism is fusing, and the electric signal is able to uh, connect. So like when it gets to like when it gets in between the say it has to go 10 miles and then another 10 miles to get to the car. Well, the first 10 miles, that's when the signal would be dragging off, and then the rest of the signal would pick up after its second 10 miles. But I'm just saying, like, yeah, they would have this, the etherists would have this metaphysical theory where, like, it's okay to have this exception to our understanding of physical laws, like a just a giant observation flaw. I mean, the fourth dimension is somewhat of a observation flaw, but you can't really. I mean, if you're predicting nuclear energy, then how can you say that the fourth dimension is? Uh, sorry, like if you are predicting the fourth dimension, okay, of time, so you're going to use quantum mechanics and you're predicting nuclear energy, then you have to just be able to accept that that's the fourth dimension. Like you're not going to be able to get out of. So I mean, that's Cartesian. That's the Cartesian principle, right? Because you have to essentially have like a hypograph or a graph where there's just essentially infinity. At least that's how I was understanding it. Um, but that's only dissolving the fifth dimension, so you're still stuck with the fourth dimension. Um, if not, he was doing two dimensional theories and actually trying to understand every bit. That seems like a little bit more correct. Like I don't think he was actually. I think he was doing up, down, left, right, but he wasn't doing forward, back. He just was doing essentially up, down, left, right, and then time is what it seemed like, because it was um, a hypergraph or a hypograph. A hypergraph because he was trying to show that the inverse law essentially could be anywhere. Descartes, in my understanding. So that makes sense. But I'm just trying to elaborate that, yeah, if you say that there's one signal from an antenna going to connect with another signal from another antenna, it's just like the Veritasium transformer recently, because you have that switch. So that switch is what is the tell. So the switch is the tell, and understanding that, yeah, the magnetism is going to go essentially where the magnetism is going to go. Like it's going to be an actual radio wave. So, but you don't want to be able to explain that for all matter, because, well, you don't want to say that the wave is all matter, so then they create the dependence laws. Okay, that's how I understand it. Like a dependence law could be a Newton gravitational constant, if you will, like just the Newtons and um, how he proved like the elliptical orbits or predicted something like the elliptical orbits. He made a sort of a I don't know what to call that, like a strange prediction that the well, like the sun's spherical, so why isn't the orbit a circle? And he discovered that it had to be an elliptical orbit, and that would be something that was creeping into like this, let's say, third dimension, or maybe even the fourth dimension, rather, for Newton. So like the tangent and the angles and things like that, and working with work and understanding that force is going to come in direct contact with work, and uh, there's going to it's and the bits are going to be manipulated. Essentially, how Descartes wouldn't have understood it because he was just saying the bits would have changed the acceleration or the velocity, vice versa. Not whatever Leibniz, but vice versa or whatever. I don't know. But yeah, acceleration, velocity. I mean, that those can both be like velocity can be conducted by, um, and that's actually really strange if you say velocity, like if the velocity of a lightning strike, sorry, not well, yeah, I mean, you're looking for insulators, right? But I mean, if you say the velocity of um, essentially you could because like the velocity is going to be, sorry, for a lightning strike, and you're dealing with velocity, and the lightning essentially wants to erupt. It wants to fuse and erupt into the sky, and sometimes, I mean, well, essentially, what are we saying? Like it's kind of like fusing like from the bottom to the top at the same time, right? I mean, we're not predicting that. That's like the whole marble, in the tube thing. So like you just push one marble and it looks like it shoots out the other side, or you push one electron and it looks like it shoots out the other side of the Milky Way galaxy or the transformer, but really you're just pushing multiple ones. So you're not really saying you're saying that work is the foundation. Newton's work is the foundation of force, like because he's predicting this force times or this force over distance. Um, and then likewise, he's also saying force, sort of, uh, sort of deducing. Okay, force now is going to equal gravity, mass one, mass two, over uh, the radius squared or distance squared. But so I mean, just deducing or uh, momentum, but the understanding that there was this idea that they were trying to, understand like what we know as a nuclear bondage, like nuclear bits bonding. They could have seen that as their deductionism. So their rational deducing from, let's say, well, just yeah, like sort of having like a just a regular or like like the light bulb, and the light bulb is magnifying out, but then what are the bits that are pushing in on the light bulb, um, that are converting or like they're decaying the bits. So the bits are becoming broken or decaying, and so like just and just putting that on sort of the Descartes hypergraph, like Newton could say, well, I'm going to deduce uh, the light bulb to be the work, and I'm going to deduce the decaying photons to uh, essentially be force, and then your magnetism, and then And then you're just understanding that the coil that's on fire or that is producing the light, you're just essentially trying to now depend on your physical understanding of the light bulb, but have it um, inverted. So I'm just saying Newton could have just added um, like that. Essentially, like he could have um, what is the word fine tuned Descartes' two dimensional understanding of the bits, and then Newton essentially has a three dimensional understanding because he can deduce force from work and gravity from force. So it goes work. So like from most accumulated kinetic energy, I mean, because you can't really play around with that because that's essentially, because if you're going to talk particles, that's, it's sort of sad, I guess. Like I'm trying to think of like how you could derive something positive from, like if you, obviously you could derive something a little bit more positive from deontology, like the philosophy of Kant. Well, for me, than traversing, ontology, like just the Maxwell or the Gödel or the heavy side, or essentially, well, not really Faraday, I guess, but you can essentially, uh, I just named way too many names. I lost my train of thought. Um, but yeah, you can just understand that there's a real deductionism happening. But it's like, well, sorry, you have like your work that has, well, yeah, like sort of if you're thinking of like a dark matter, if you're just thinking of like, okay, dark matter instead of kinetic energy, because I am disappointed to say, but maybe just a little bit more evolved in my thinking than Leibniz to be able to like say, okay, well, we have bits now, and if we are dealing with bits, and you are trying to like understand the totality of um, Earth's gravitational pull and all of the actual bits that are essentially making up all of the elements, like on the periodic timetable. That's why they have their entropy and their nuclear fission inverted. So they have the lowest amount of entropy when the fission, when everything is fizzing. Um, that's essentially what they're understanding. And then when it fuses, that's when the energy is released, and that's the big nuclear fusion. Is essentially how I am looking at it, but it's not too. I don't know if that's understandable or not, but I'm just saying, uh, it's like if you. So I'm just saying if you understand that the smaller mass, the smaller bit, and just pretend it's the moon, like for Leibniz, just pretend it's the moon, and you're just saying, well, the moon has more energy than Earth. Because essentially, Darwin Darwinism could have proved, or biological evolutionary biology rather, could have proved that we evolution would have never started without the moon. I think that's really like an essential piece to the story, and so just the understanding that okay, Leibniz is creating, like as I was kind of saying, Newton's sort of linear third dimensional view of reality could have been um, a just a refining of Descartes, and essentially Descartes kind of like not knowing what to do with this dielectric effect, and Newton understanding that, well, the entirety of the dielectric effect can have it can just be a nuclear fusion, how we would understand it or how we would say. So therefore, it already exists that the matter, essentially between the two antennas, they are already fusing. Essentially, like all you have to do is just propel energy through them. Like essentially, I'm just saying, like sort of in a classical mechanical way, you could say that Newton had already proposed a dielectric effect, and like prior to the 1800s, prior to Faraday. Um, because he was already understanding like this deduction process again with force and gravity. Like he knew that gravity had to be deduced and it had to have mass and weight. So, and then you get to the Faraday paradox, and that's when you're sort of like really dipping into the kinetic energy, I would say, because just uh, you're obviously just essentially making up energy. I'm just not sure. Logically, the only way that you want to say there is a small amount of energy that is going to shock absorb the whole conductor, that is going to be able to actually derive the nuclear fusion. So you're saying the nuclear fusion is derived, or is it at least, this is like the Veritasium thing now. So the Faraday paradox, the energy is going to basically enter the conductor, or the conductor, and that's going to begin the fission process, the fissioning, the nuclear fission, and so yeah, it's just going to get fuse the hell out of, and when it actually or when it actually is contained enough nuclear fission, like it's contained enough. Look, I'm just saying with the again, I'm just saying like mechanically, the static state uh, fission understanding is that the atoms are losing shape. So these atoms are losing shape. It makes sense to say that as they're losing shape, there is more. Well, understanding the temperature. You're talking about like the lowest energy, but we just say we're dealing with. We can just say we're dealing with the smallest piece of matter that we can imagine, and those bits are heating up, but they're not heating up to the point where we can understand them. Like if we get a shock, we're essentially getting burned. Um, you get like burned by lightning, and that's essentially because, uh, according to lower entropy, the entropy was broken down so much uh, because there was just a dielectric or whatever, and it wasn't able to fully fuse. Like, and then so it cools down when it fuses. But essentially, like it's still. Because essentially there has to be a difference between. It's almost like they're talking about potential temperature, which is free energy, of course. Um, but if it's potential temperature, okay, does that mean, all right, if it's not potential energy, it's potential temperature. So does that mean that essentially, we are talking about like, I guess maybe that's like just a better way to look at it. Like just there's more potential decay that is going to happen, since when they are when there's nuclear fission between the bits, they're breaking apart, they're losing their shape, um, it's unbalanced, and that's the so it's theoretically saying, well, there's no entropy happening there, because entropy can only happen in something with a very solid state, like a very static um, jolt of electricity is experiencing a cooler, or like a cool down of a potentially higher um, temperature. So you're not saying that the nuclear fission, okay, when everything's breaking down in the magnetism and there's not the electric fusion yet, you're not saying that there's potential energy there. If you say there's uh, potential temperature, okay, you're talking about free energy, of course, but yeah, you're just trying to adapt uh, the temperature to, when it fuses, essentially it's just cooling. So it's not really saying that doesn't hold, but that doesn't, break the laws of physics if you just have a potential temperature, right? Um, Understandably, the static state Big Bang does have a legitimate temperature, but I'm just saying, or it does have like a legitimate scale, like it is scalar. It's like 20 billion degrees Kelvin, and our sun's 4 million degrees Kelvin, 4 million Kelvin. So that's a huge difference. But they're just saying, well, there's that much potential energy. There's that much potential uh, temperature. That's kind of hard to say in the nuclear physics of our sun. Now, I'm not saying the sun can go up to 20 billion Kelvin, but maybe it can go up. Well, it can grow and all that, and uh, but I think that's just a better way to maybe look at it, like just potential temperature in the static state Big Bang. Um, so yeah, it's not like totally, I guess, flawless because yeah, you're just this is just sort of again doing the fourth dimensional thing because yeah, you don't really have anything with kinetic energy, but when you actually get to the fourth dimensional state, you're getting to the fourth dimensional state, understanding this quantum gravity effect, and that the bits when they spread apart, they essentially have to be. I got to understand what how to say fission correctly, but they're fissioning, and that means that they're holding more potential temperature. They're not holding more potential. I mean, because if you say potential energy, then what are you really talking about? But with temperature, okay, not necessarily talking about free energy, but we can just understand decay, and that's my point because um, as things like as a lightning bolt expires, there's going to be a cooldown. So there was a jolt of energy, or there was a nuclear fusion, and then there was a cooldown. So, but the quantizing or understanding, like quantum mechanically, that the fissioning process of the nuclear bits did happen. You can say, that was the potential temperature or decay particles that were uh, that were combining. So I don't know if that can be refined or not. Yeah. So I think that's a lot better than trying to jump on to string theory. I mean, I can't really derive anything from string theory. I mean, I like the static state Big Bang, but essentially the string, like, correct me if I'm wrong, but string theory was after um, static state, and now string theory is somehow supposed to prove like cosmic inflation deflation, and or like it's like the cosmic sort of dip, because you have this, again, this really low entropy. Well, you have zero entropy and maximum temperature, and then you have full entropy and minimal, uh, almost like minimal decay. So it's decaying the whole time. So you go from temperature to decay and just entropy. So yeah, temperature decays the bits, or temperature is the potential energy for uh, cosmic deflation, and entropy is just a constant in cosmic inflation, and that's how you have this basically, like just an X. Um, oh, essentially, yeah, just a Cartesian infinite understanding of how, or I guess an infinite understand, like a Cartesian infinite understanding that might that might work. For a three dimensional for Newton, um, you have to work with mass and you have to work with weight. So how many bits are in each mass, and where's the work, and how is the force having an effect on the work. And if I'm trying to conserve energy, then you get into Einstein's fourth dimension, and yeah, you just magnify smaller and smaller, and you go from mass and weight and force uh, and the work to essentially trying to understand that full spectrum that is that time dimension, like that infinite time dimension, where all of the bits are particleized, and you see every particular, I guess, uh, space or sorry, like yeah, separation or the non-separation between all the bits. So again, non-separation in Einstein space is going to be a bigger mass, and more separation in Einstein space is going to be less mass, but it's going to have more potential to eradicate or decay, like radioactive decay, essentially, for your fourth dimension. But then how, like, for because again, you can, and the only way you can, I think, get any, like, the only way you can make a metaphysical argument out of essentially like an Einstein 4D and a sorry, uh, Newtonian 3D would be something like the Faraday paradox, or like the Maxwell. And it's like all these, like, confined and Higgs and Coulomb atoms, like which atoms, what atoms do you want to use today, like the CGI ones, or the round spherical ones, or the ones that have like the shock waves or whatever. I mean, I see it more as like shock waves. I see like the universe is made out of shock waves. And as you get further and further away from Earth's gravity, as you pull away from the core of the Earth, like uh, not including the moon, like the shock wave just expands, but it's just a bigger shock wave. Like I think that's kind of like dark matter. I mean, I think it should be more of a shock wave than a superfluid, because that's really dangerous to say. Well, it's a superfluid, but it doesn't have any potential. It doesn't have any potential radioactive decay on the mass. In this case, Earth. So there's no, like, I mean, well, yeah, like what's a superfluid going to do in gravity? I mean, if it's holding potential temperature, aka potential energy, like if that little piece of superfluid wasn't there, then the entire universe would fall apart, right? Um, what is that? What is a superfluid going to do? Is my point. Like, I mean, but if it's a shock wave, or it's some sort of potential energy, or um, its potential decay, like upon the gravitational force, or quantum gravity, or three dimensions, whatever, then it's like a little different. Well, it changes. I guess it changes the game. Not thinking like, because I mean, if you're just thinking of like the background, if you're thinking of quantum mechanics, you're thinking of like the background, what's happening, what's playing, what's going on in the background. Essentially, you're not thinking about what's happening. Like I'm sorry, you're going backstage, and like there's a play happening. That's cosmic religion, and then like you go backstage and you just sort of look at the audience, and you look at the play happening, and that's sort of what I'm sensing as Like, I mean, you could look at it as like, they could turn or something. I mean, like the backstage managers or something could, just ruin the whole show or something. I mean, it's just I'm just calling it like potential energy in the sense that okay, they have uh potential, decay rates. They have I mean, it's just there. It's just holding, I guess, the universe conceptually together. So, yeah, I mean, I don't know how much further I can take that. Um, yeah, definitely, I definitely didn't hit, too much of the extinction stuff. I'm still pretty on board with chronological selectivity, except when uh, when it comes to diversification. I mean, I still think there's a lot of Caucasians and stuff like that. It would just it'd be pretty logical to say that yeah, there was diversity happening with the Neanderthal. But just my point is that just like our shades of skin at the very least, like our pigmentation, and that we were in different climates, and that would sort of uh, that would sort of change the game in terms of natural selection if we were to still continue, like I mean, to have an actual Ubermensch where there was actual like pure diversity, say in like 900 years, and I mean that would be like the potentiality or something. Like it just be sort of well, I don't know. I mean, just naive to think that we would be or we would not be the last uh, animal, like the last sentient biological species on the planet. I mean, I mean, we just have all the technology. I mean, it just is like clear as nothing. And yeah, so I don't think, but I don't think that that's how people think about it. People think like, oh, we're gonna, evolve gills and we're gonna like, whatever. I mean, just it's it's that whatever I don't know 250-year cycle thing in the Bhagavad Gita. I don't know, the Kali Yuga. Yeah, that's what it is. Like the Kali Yuga is saying that we're in a 250 million. Is it 200? Yeah, 250 million year cycle in the Milky Way galaxy right now. That's out of the Bhagavad Gita, and so 250 million years. Okay, that's what I was talking about. I was talking about the Kali Yuga when I was talking about humanomaniates, humanomanians. Sorry, just that's the Kali Yuga. 250 million years we got. And we're supposed to be on Saturn by then. Venus doesn't matter. Like we've conquered the solar system, and we're just gonna hang out. I think yeah, we just hang out for like eons on Saturn. Like that's the tale. Like that's the story or something. Um, which is, I mean, it's just crazy that they have a. I mean, they have like they have a 250 million years in the future, but they don't have anything in the past. It's kind of funny. Um, so yeah, I mean, not even the Bible's that bad. I don't even think the Bible has. Where do people get all this stuff? Like, where's 10,000 BC? I mean, all you get is like just paragraphs and paragraphs and paragraphs of names. Like I was just telling my nurse yesterday, like, that, I mean, there's like three decent books. Like, I mean, if I could only like choose three like books out of the Bible, I'd know which ones I'd choose. But yeah, I mean, other than that, like, it's just like paragraphs and like almost like half a page of names and like, oh man, it was so bad. Like, so those are all like those are all the ancestors and but no years or anything like that. And then I never saw anything about like well, like where's all this pagan stuff come from? I never saw anything like about like crucifixion or anything. I mean, I never there was never like this like the chapter about the crucifixion. I was always looking for that chapter where he gets like like you know, mortally crucified or mortally tortured. And there was never that story. There was just always like all this, crypto bullshit. Uh, yeah, I mean, just there was never like I don't know. I mean, there was a bunch of like fucking bullshit passages and stuff, I guess. But I mean, there was never like hardcore uh Mel Gibson shit type shit going on. So that's what I just never got about it. Yeah, it's like there's like the cult of John 3:16, and like with there's like 10 different ways you can like say forgiveness or trespasses or like it's debtors. And so yeah, just it just totally got butchered. But well, it just butchered everything, I guess. It just butchered enough to sort of dilute critical thinking, I guess, or enough. Yeah. So, but yeah, there's I don't know, prokaryotes to eukaryotes. It's just, I mean, that's a lot of. I mean, it's just a lot of years. It's just way too many years to sort of discount like a critical idea, understanding of. Maybe it's like extremely unrelatable for people. Um, I think that could be a easy, I don't know, an easy way to be, uh, what is it, just misinformed, disinformed, um, especially with like tribes in South America and stuff. But yeah, so there's just like there's just no talk about like, oh, we've been everybody's evolving, but then yeah, that's not the idea. Like um we're all who we are, now. So we don't have like any sort of desire. I mean, we don't. I mean, we don't like. There's no conversation anywhere about like you know evolution. I mean, it's forbidden. Like yeah. I mean, it's a joke. Oh yeah, yeah. Everybody knows we've been here for 4 billion years. Whatever. Who cares? There's only been six mass extinctions. I don't know, 99.999% of species that have ever evolved went extinct. So we don't have that good of a chance, but oh well. And yeah, it just gets no uh, publicity or press or anything like that. It's just 7 24/7, 365. So yeah, I didn't think that was too bad. I don't know what I'm gonna call this one yet. Yes, just a nicer way to say energy, just or sorry, potential energy. So it's just potential uh, temperature.